Our next presentation is on BAR-SAV for source address validation and BGP prefix filtering. It's Igor Lubashev is a director of engineering at Akamai Technologies, where he leads teams focused on Linux and kernel operating systems, load balancing, and edge virtualization systems. He's played a key role in launching Akamai's Anycast CDN and distributed Linode cloud products. Active in the IETF, Igor has contributed to the development of the QUIC protocol and innovative loss measurement techniques for QUIC. He is currently focusing on the problem of source address validation. He is a frequent speaker at industry conferences, including IETF and Networking at Scale, where he shares insights in networking performance and system architecture. A graduate of Massachusetts Institute of Technology, Igor has a deep technical background in networking and in distributed systems. This is Igor's first time presenting at NANOG, and it's a pleasure to have him speaking remotely. So thank you.
All right. Good morning, NANOG. Thank you for nice long bio. I'm here today to talk to you about a new source address validation technique we developed that we call BAR-SAV. Actually, it was supposed to be not me, but Sriram, who is our lead author, who was going to talk to you about it in person. But he works for NIST, and we all heard about US government shutdown, so he cannot be here, and you have me instead. All right. What is BAR-SAV? It stands for source address validation using BGP, ASPA, and ROA. It's basically a method for mitigating IP spoofing in complex networking technologies, and obviously trying to minimize or completely reduce what we call improper block, which is blocking of legitimate traffic. It's, in essence, a method for ISPs to discover a customer cone and a set of prefixes that are originated within that customer cone for each of the customers and lateral peers. So it's useful for SAV. In some cases, it can be also useful for prefix filtering. Now, and I promise this is my last and only marketing slide for BAR-SAV. We're going to get into technical details after. But just to motivate why somebody should care, people have been caring about blocking spoof traffic for a while, all the time from BCP 38 to the latest RFC 8704. And currently there is a relatively new working group at IETF called SAVnet that focused on the topic of blocking spoof traffic on the internet. BAR-SAV is right now it is a draft in SAVnet. It's the most advanced, closest thing that we have, like the most advanced state of the art we have in terms of a draft. It does significantly improve ability to detect hidden prefixes, so complex networking environments where networks are doing traffic engineering and all the other techniques. It provides a solution to direct server return. We'll talk about it more. And its goal is to block spoof traffic coming from customers and lateral peers. And it is a recommendation, both ours and many other people, that the best place to block spoof traffic is early, basically early before it enters the core of the internet. Doing it later becomes much harder. We do have in the draft some recommendations for doing SAV on provider interfaces. We're not going to talk about it today. Obviously, the set of things we can do there is more limited, but if you're very interested, read the draft. The advantage of BAR-SAV is in its deployability, which basically means there is no change to any protocol on the wire. And that means that it offers early adopters all the benefits. So you're not dependent on somebody else to do something, so that if you want to deploy BAR-SAV, you can immediately do it and get whatever benefits BAR-SAV offers you. Okay. So first, let's look at the current state of the art, which is RFC 8704, Enhanced Feasible Path URPF technique. What it says is a prefix should be considered valid as a source prefix on an interface if there is at least one prefix that shares the same origin AS number that is feasible on this interface. So let's look at an example here. We have AS1 that has two providers, AS2 and AS3. AS2 also has AS3 as a provider. It also has AS4. AS1 has two prefixes to announce, P1 and Q1. AS2 has its own prefix P2. AS1 is announcing P1 to everybody, and for whatever reasons it's announcing Q2 only to AS3. And AS2 is also only announcing its own P2 to AS3, but the prefix it got from its customer P1 it announces to everybody. And now we have AS4 that's trying to calculate the source address prefix list that allowed an interface from AS2. So prefix 1, it directly receives BGP announcements on it, no question there. Q1, it shares the same AS1 as an origin AS. Q1 it did not receive from AS2, it received it from AS3, but that doesn't matter. The RFC 8704 says if you share origin AS with something that's already feasible on this interface, you're good too. So Q1 is discovered. P1, however, is not discovered. So because nothing shares that is feasible on the interface from AS2 shares AS2 as the feasible path, as the origin of a feasible path. So the current technique will miss P2. Now, BAR-SAV also improves just without even looking at those other things like ASPA and ROA, processing of BGP path advertisements. So BAR-SAV would, in this scenario, would discover P2 because instead of just looking at origin AS, BAR-SAV will look at the entire AS path and say, if any AS on AS path from a feasible path shares an AS from any other prefix, that other prefix is allowed. So in this case, prefix 2 has AS2 on its AS path, and prefix 1 also has AS2, not an origin, but doesn't matter. And therefore, prefix 2 would be discovered by BAR-SAV. Well, that's great. What if AS1 published prefix 1 to AS2 with no export? In that case, AS2 would have nothing to announce to AS4, and that BGP signal would just not be available. There would be no feasible path from AS4 perspective on the interface with AS2. So that basically shows that information that purely based on BGP is not going to be ever sufficient. What do we do with BAR-SAV? Well, we look at RPKI registry, we look at ASPA and ROA as well for source of information. So in essence, BAR-SAV uses BGP, ASPA, and ROA to discover customer cone for a particular customer lateral peer. And once the customer cone, which is basically a set of all AS numbers that are in this customer cone, once that customer cone is known, we're discovering all prefixes that are associated with that customer cone, that are originated by that customer cone. Again, the sources of information are like BGP updates, so that's just the same as with the current 8704, except we're looking at all AS numbers on ASPA. We're also looking at ASPA, which is a new RPKI object that is just about to be released as an RFC that lists providers for an AS. And we're looking at ROAs. Those are existing RPKI objects, and they're getting quite a bit of adoption already. That list origin AS for IP prefixes. And the end result, the end goal of BAR-SAV is creating per interface subtables. So allow lists per interface. Just to highlight, it is the same algorithm that would be used for CFO AS7 to discover its to create an allow list for the interface with AS6, no matter whether AS6 is a customer or it's a lateral peer. So again, same algorithm for peers or customers. Okay, how do we do that? BAR-SAV draft has actually two algorithms. One we call procedure X, and this is a procedure for maybe faraway future when ASPA and ROA are completely ubiquitous. But it could be actually not that far away future if your particular AS knows that a customer cone, somebody's customer cone has a ubiquitous adoption of ROA and ASPA. So in that case, you could use it. But I'm looking at it mostly from, this is a future kind of thing. Every single customer provider relationship is reflected in ASPA, and all prefixes advertised are reflected in ROAs. If that's the case, it becomes pretty simple stuff. We don't even need BGP, as you could notice. We obtain a set of ASNs in the customer cone using ASPA. Once we have that, we gather all prefixes in ROA that are associated with those ASNs that we just discovered. Add to that maybe some locally administered allow list, and you have the SAV filter for a particular interface. All right, that's great. But the reality is it's gonna take quite a bit of time for ASPA and ROA to be ubiquitous. Meanwhile, we have the internet we have. So BAR-SAV compensates by using BGP updates to infer additional data. Okay, so the updated algorithm basically it still has a very similar structure. First, we discover customer cone by using not just ASPA but also ASPA from BGP messages, and we'll talk about it more details how that's done right after. Once we have the customer cone, we gather all prefixes that are available in ROA. We gather additional prefixes that are not in ROA, but we can infer from BGP update messages. So the prefixes that are originated within the customer cone. We combine the two sets of prefixes, add a locally administered allow list, and we have the permissible prefix list for the interface. Okay, how do we compute the customer cone using ASPA and BGP? it's basically done iteratively in effectively breadth first search way. We start with AS number of that immediate neighbor that we're considering. And then the iterative step is that for every AS discovered, so starting with just one, so every new AS discovered that belongs to a customer cone, we look at both ASPA and ASPA to discover customers of that newly discovered AS. So looking at ASPA, we find all the ASs that are listed, that list the newly discovered AS as providers. So they're the customers. And using ASPA, we find ASs that come before the newly discovered ASs in ASPath. And again, we're looking at the entire RIB. So when looking at BGP updates that have been received on any interface. So as we discover new ASs that way, we repeat step 2 until we cannot discover anything anymore, at which point we have discovered the entire customer code. Obviously, that just highlights. We have a lot more details. Read the draft for details. Direct server return is one of those complex networking scenarios. That's something that we implemented at Akamai roughly 10 years ago, and that's the case that was initially something that made me interested in this entire topic. And BAR-SAV helps with this, but just to understand what we're talking about here for direct server return, you have anycast pubs all over the internet that announce anycast VIPs, and users connect to those VIPs, whatever is closest to them, whatever pub is closest to them. That location has no content. It's basically acting like a very fancy pseudo router. It's looking at where the user is. It's looking at what content it's trying to get, and it forwards the request to an edge CDN node that actually has the content that's close to the user. And that edge CDN node sends the data, the basically bulk of the video download, directly to the end user. You effectively have this triangle on the internet. So same idea, just in this sort of more network focused diagram. You have AS1, that's your anycast that's your AS that has anycast CDN nodes. The anycast prefix is prefix 9. So you have a user who is sending a packet to prefix 9. It's received by AS1, which decides that the CDN node to serve the traffic should be in AS2. It tunnels basically all the request headers X over something like AP and AP from AS2 to from AS1 to AS2, and AS2 is completing the reply for this connection, TCP or QUIC, whatever it is, directly to the end user. Now, for the connection to work, AS2 has to send its packets claiming to come from prefix 9, because that's the connection that end user has. AS2 never advertised prefix 9 to anybody. So if its provider, AS3, is trying to do source address validation on the interface with AS2, it needs to know something about prefix 9. Otherwise, it will block it. The recommendation here we have is, if they're using BAR-SAV, the CDN should publish a ROA that says that prefix 9 can be advertised from both AS1 and AS2. Now, AS1 will advertise prefix 9. That's its entire point in life, to advertise any cast prefixes. AS2 never plans to advertise prefix 9, but because there is ROA, BAR-SAV algorithm will discover that prefix 9 is associated with AS2 and authorized to be used by it, and AS3 will include prefix 9 into its allow list on the interface with AS2. So, effectively, the complex scenarios with DSR and no exports, BAR-SAV recommends that you use, you publish ASPA if you're using no export towards some AS, towards some AS. Basically, if you use no export towards in an advertisement to your provider, you make sure that you list your provider in ASPA. And if you're using DSR, you just list those prefixes, any cast prefixes, for example, in ROA from that associated with autonomous systems from which you will actually originate these packets. The alternative, of course, is also to advertise less specific prefixes. But anyway, using ASPA for NROA is a good thing. Is a good thing for ensuring routing security, and it's also a good thing for ensuring source address validation works. Again, some recommendations that we have for networks that want to use RPKI, and they hold both as good principles to use just in general when you use RPKI for the purposes of route security and for the purposes of source address validation, which is basically comes down to make before you break. If you have an existing prefix in ROA, wait until your new row is proper, and you want to like change row, split it. Wait until the new row has propagated before you withdraw the original prefix. If you got a new transit provider, and wait until ASPA has propagated before you start using that transit provider. So continue using the old one until RPKI has been updated and its propagation is propagated to all the users. Now, so far, you probably noticed that all the signals we've been talking about for source address validation have not been developed for this purpose. All the signals like BGP update messages, ASPA, ROA, all of that has been developed for routing. And that's been the case for everything that source address validation techniques have been using at this point. Right now at IETF, there is a new interesting proposal to create a specific RPKI object that's actually designed for source address validation, which is called TOA, or Traffic Origin Authorization. Effectively, what this object would do, it would authorize sending traffic from a particular, using IP addresses to originate from a particular AS, but not for that particular AS to announce them. It is expected that, of course, if you have a ROA, which allows the announcement, it kind of implies that you're also allowed to originate from it. So I don't expect that there would be many prefixes registered with TOA, but there could be some. So DSR case, for example, could use TOR once it's available. So this is right now a work in subnet working group. If it does advance into an RFC, it will be very easy for BAR-SAV to incorporate this source of information. Of course, before TOR is a thing, we recommend using RAW instead. And now, so far, we've been talking about using BAR-SAV for source address validation, for basically creating prefix lists for blocking spoof traffic. That's what it was developed for. But as a set of techniques, I mean, it's basically a set of techniques that let a network figure out customers, its customers and its customer and peers' customers and prefixes originated by them. It can still be useful as a technique, as an information source, even if you are not planning immediately to use it for blocking spoof traffic. And if the adoption of RPKI, so for RAW and ASPA, is ubiquitous or kind of very widespread within your customer cone, for example, if you know that, then you could actually use that information that you can glean from BAR-SAV principles to perform prefix filtering. So if you know that you've got all the information about allowed prefixes from RPKI, you can use it to filter your BGP. And that's the end of the content I have for today. Obviously, any questions? Welcome.
All right, thank you, Igor. That was a great presentation. Do we have any questions from anyone? Okay.